Finding limits graphically and numerically. Consider the function f of x is equal to the quantity x cubed minus 1 divided by the quantity x minus 1. You'll notice that if x is equal to 1, you get a 0 in the denominator here, and 1 minus 1 is 0, and we know you cannot divide by 0, so this function does not have a value when x is equal to 1, and that's shown here on the graph because there's an open circle where x would equal 1. So when x is equal 1, there's no value. So we can't talk about the f of 1 because there is no f of 1, but what we can discuss is the limit as x approaches 1, or as x gets closer and closer to 1. So let's look at what happens as x gets closer and closer to 1 from the left side. So here's 1, here's a point on the left side of that, and as you get closer and closer to 1, you'll notice that first it goes down, and then it gets closer and closer to what seems to be the value of 3 on the y-axis. So I could say as x approaches 1 from the left side, the y values are getting closer and closer and closer to the number 3. Let's get a better estimate by using a table. Now we're really close to 1 on the x-axis. Let's use a table where the x values are getting closer and closer and closer to 1 and see what the y values are getting closer and closer to, if they're getting closer and closer to anything at all. First, I'll plug 0.9 into the function. 0.9 is pretty close to the 1, but still less than 1. So when I plug in 0.9, I get 2.71. Now let's plug in a number even closer to 1, like 0.99. Even closer to 1, but still less than 1. So it's still on the left side of 1. When I plug that in, I get 2.9701, a number that's even closer to 3 than 2.71. So now let's plug in a number that's even closer to 1, but still less than 1, like 0.999. When I plug in 0.999, I get 2.9970, which is even closer to 3, and the distance between 2.9970 and 2.9701 is smaller than the distance from 2.9701 to 2.71. So not only are we getting closer to 3, but the distance between the outputs is getting smaller, making it even further seem as though this thing is converging on the number 3. So let's plug in one more number. Let's plug in 0.9999, and when you plug that into the function, we get 2.9997, which is even closer to 3 than 2.9970, and is closer to 2.9970 than 2.9970 is to 2.9701. So these consecutive y values are closer and closer together, but also getting closer and closer to the number 3, and therefore we can say that as x, or we can estimate that as x approaches 1 from the left, the y values, or the f of x, seems to be approaching 3. There's notation we're going to use for this. Let's introduce this limit notation. This is read that the limit LIM, the limit as x approaches 1 from the left side of f of x, that same function, is equal to 3. That encapsulates everything we've just discussed, the table and the graph, what we've seen visually, about what happens when you get closer and closer and closer to 1 on the x-axis from the left side. All right, now let's see what happens if we approach from the right. So there's the point, and we're going to get closer and closer and closer to 1 on the x-axis, and look at what's happening to y. Well, still looks like y is getting closer and closer to 3, but now instead of numbers that are smaller than 3 getting larger and approaching 3, now it looks like we have numbers larger than 3 getting smaller and approaching 3. Let's see if that pans out on a table. So here are some x values that are approaching 1 from the right. So 1.1 is pretty close to 1, but still bigger than 1. 1.01 is even closer, but still larger. 1.001, closer, but still larger. 1.0001, closer to 1, but still bigger than 1. What happens when we plug in 1.1? We get 3.31. Pretty close to 3. What happens when we put in 1.01? Well, we get 3.0301, even closer to 3 than 3.31. When we plug in 1.001, we get 3.0030, which is even closer to 3 than 3.0301. And when we plug in 1.0001, we get 3.0003, very, very close to 3. So we can approximate that as x approaches 1 from the right, the y values, or the f of x, approaches 3. There's notation for this also. We would say that the limit as x approaches 1 from the right of f of x is equal to 3. You'll notice we changed that superscript from a negative symbol to a positive symbol, and that's to signify that we're approaching 1 from the right side as opposed to from the left side. So what does this mean? Well, because of the fact that the limit as x approaches 1 from the left of f of x is the same as the limit as x approaches 1 from the right of f of x, they're both equal to 3. Because that's true, we can say the overall limit as x approaches 1 of f of x is equal to 3. So this symbol says that both the left limit and the right limit are equal to each other. If the left limit and the right limit are not equal to each other, then this overall limit does not exist. Let's take a look at another example. Let's consider the function f of x equals the quantity absolute value of x minus 2 divided by the quantity x minus 2. Well, let's approach 2 from the left first. So here's the value 2 on the x-axis, and here's a point that's going to approach 2 from the left. As you see, it's going horizontally towards 2, and the y value is always -1. So if we were to make a table and plug in numbers that are getting closer and closer to 2 but are smaller than 2, so approaching 2 from the left side, when we plug in 1.9 we get -1. When we plug in 1.99 we'd get -1. When we plug in 1.999 we'd get -1. When we plug in 1.9999, we get -1. So it doesn't matter what x value you plug in here, as long as that x value is on the left of 2, the answer, the outcome, is going to be -1. Y values approach -1 as the x value approaches 2 from the left. So now let's take a look at the notation for that. Once again, the limit as x approaches 2 from the left of f of x is equal to -1. That's the correct notation. Let's see what happens when x approaches 2 from the right. So as x approaches 2 from the right, as you can see, the y values are on the same horizontal line at +1. On the table, it would look like this. As x approaches 2 from the right, you choose numbers that are bigger than 2, but getting gradually closer to 2, like 2.1, but 2.01 is even closer, 2.001 is even closer, 2.0001 is even closer. So we're approaching 2 from the right now. Well, when you plug in 2.1, you get 1. Plug in 2.01, you also get 1. 2.001, you get 1 again. 2.0001, you get 1 again. We can approximate the limit as x approaches 2 from the right to equal 1. And the notation would say the limit as x approaches 2 from the right of f of x is equal to 1. All right, what does that mean? Well, in this case, because the limit as x approaches 2 from the left of f of x is -1, while the limit as x approaches 2 from the right of f of x is +1, and -1 and +1 are not equal to each other, because they're not equal, the left-handed and the right-handed limit, we say overall the limit does not exist. So in order for a limit to exist, the left-handed limit and the right-handed limit have to equal to each other. Because the left-sided limit and the right-sided limit are not equal, we say overall this limit does not exist. So this is the first instance we've seen of a limit not existing. There are different ways for a limit to not exist. One of them is if the limit from the left and the limit from the right don't equal each other. Another way for a limit to not exist is this behavior here that we're going to see as x approaches +1. So let's consider the function f of x equals 1 divided by x minus 1. As you can see, this function is not defined when x is equal to +1, because if you plug in +1, you get 1 minus 1 in the denominator, and you can't divide by 0. 1 minus 1 is 0. So let's see what happens as we approach 1 from the left side. So here's a point. Let's approach 1 from the left, and as you can see, that point just keeps dropping drastically, approaching this vertical asymptote here. Let's use a table. As x approaches 1 from the left, so we're looking at numbers like 0.9, 0.99, 0.999, 0.9999, and when I plug in 0.9 into this expression, I get negative 10. When I plug in 0.99, I get negative 100. When I plug in 0.999, I get negative 1,000. So not only are they not converging on a specific number, but the distance between consecutive y values seems to be getting larger. The distance between negative 10 and negative 100 is 90, while the difference between negative 1,000 and negative 100 is 900. When I plug in 0.9999, I get negative 10,000. So the distance between consecutive y values is growing. So this is not converging on a single number. The y values just seem to be getting smaller and smaller and smaller. So this thing is unbounded as x approaches 1 from the left. It seems as though as x approaches 1 from the left, the y values are dipping down to negative infinity, just dropping drastically. What does that mean? What that means is that because the limit as x approaches 1 from the left of f of x is unbounded, going down to negative infinity, that's another reason why a limit might not exist. So far, limits don't exist if you approach a different number from the left side than you do from the right side. And limits also don't exist at vertical asymptotes, because at vertical asymptotes, the y value either drop down unbounded to negative infinity, or as you can see from the right side here, they would climb up to positive infinity and just keep climbing. Two cases where limits don't exist. One is where you're approaching a different number from the left and from the right, and another is where you have unbounded behavior because you have a vertical asymptote. Last example, let's take a look and consider the function f of x equals the sine of 1 over x. And here you can see a little graph of the function there. Let's do the table first in this case and see what happens with the table. So let's approach 0, because here we have 0 as the place where this would be undefined. 1 divided by 0 would be undefined. Let's approach 0 from the left. So these are numbers getting closer and closer to 0 from the left. Negative 0.1 is close to 0, but less than 0. Negative 0.01 is close to 0, but on the left of 0 and closer than negative 0.1. Negative 0.001 is on the left of 0, smaller than 0, but still closer than negative 0.1, or negative 0.01, I should say. And this number is even closer to 0, but still smaller than 0. So when we plug in values, plugging in negative 0.1, I get 0.540. Plugging in negative 0.01, I get negative 0.5064. It looks like it might be converging on something. Then when I plug in negative 0.001, oh, this goes to negative 0.826. So these look like they might have been converging on something, but then this one goes all the way down to the negative side. When I plug in 0.0001, I can now get 0.3056. So it doesn't seem to be converging on anything, but it also doesn't seem to be blowing up or dropping down to negative infinity. It looks to me like these values are oscillating wildly, just very random. So let's see as we approach, and then it's just going to bounce up and down. So what does this bouncing behavior mean? Well, this bouncing behavior is what we call oscillation. The closer you get to 0 from the left, the faster this thing is going to oscillate. So that's a third way that a limit might not exist. The limit doesn't exist if the function oscillates as you get closer to the value. So the limit as x approaches 0 from the left of f of x here, well, it's not converging on a single number, nor is it blowing up to positive infinity or negative infinity. This is oscillating behavior. So therefore, this type of limit does not exist either. So those are the three ways that we say limits do not exist. A limit doesn't exist if you approach a different number from the left and right. if it's unbounded, going to either positive or negative infinity, or if it just oscillates wildly, bouncing up and down between two values like this one is doing here. That's how we analyze limits graphically and numerically.